So today we get to start Unit 3, and we're going to start out talking about some basic geometry. Now we've mentioned some of these basics before, but we're going to go over them again to develop a new set of concepts. As we've mentioned before, the most basic concept in geometry is that thing right there, a point. Just marks the location. It has 0 dimensions. A dimension can be thought of a couple of different ways. It can be thought of as like a degree of freedom or ability to move. You can't move in any direction on that point, so it's 0 dimensions. Or there's no measurements. You can't measure any lengths in any direction. So it's, again, 0 dimensions. But as we mentioned last semester when we talked about areas and volumes, everything in math, everything in geometry is created from a point. Then we can take that point and move it in a single direction. We created that line segment. Again, we often call it a line, but a true line goes on forever in both directions. In practice, a line segment is a more useful construct, but we do often refer to it as just a line. And the length of that line was just equal to the distance moved. If I take a line, or I take that point, I should say, and I go in a single direction and I keep going, I create a ray. A ray is completely defined by 2 things. The first is that starting point. Often referred to as the initial point. The second is the direction. The direction is going to be a little bit more difficult to define. Let me do another little picture of a ray here. Let's say it goes like that. To define its direction, what we use is like a navigational compass rose. North, south, east, west. The east direction is defined to be 0 degrees. The north direction is defined to be 90, 180, 270, and then back around to 0 would be 360 degrees. A compass, actually, I believe for navigation now they start with 0 degrees at the north position, if I remember right. But this is an old version of it. So obviously that starting point of our ray is at the center of that grid. We can see that this ray is between 0 and 90 degrees. Looking at it, let's just say that it's at 38 degrees. So that ray starts at that point and goes in a direction of 38 degrees. Why is that important? Well, because what we're going to be looking at here today and the next couple of days is, let's say we go back to that same starting point and we create another ray in a slightly different direction. That ray also has a direction. Let's say that direction is 71 degrees. When 2 rays have the same starting point, first of all, that starting point is called a vertex. So a point that serves as the starting point for more than one ray is called a vertex. And the 2 rays together form what's called an angle. The size of the angle is equal to the difference in direction of the 2 rays. So here, one of them is at 71 degrees, one of them is at 38 degrees. The difference is 33 degrees. This angle here is 33 degrees. That was the original definition of an angle, difference in direction. Now, through time, people have become less familiar with navigation and stuff like this. So this whole idea of having a compass set up with degrees on it has become less and less common knowledge. At one point, a large majority of the population did understand navigation like that. We don't anymore. So we've come up with an alternative definition. If I start going in a single direction and I turn all the way around so that I'm back going in that same direction, how far did I turn? 360 degrees. A full circle or a full turn is 360 degrees. If I'm going in a certain direction and I turn so that I'm now going in exactly the opposite direction, how far did I turn? 180. Where do we get the 180 from? You got it. Half of 360. Because that's half of a full turn. It's half of 360 degrees. If we're going in a single direction and we turn so that we're now going exactly off to one side. If I put a little square in the corner, it's indicating that's a square corner. How many degrees is that? 90. Again, where did the 90 come from? There you go. 360, a full turn, it's only a quarter of a full turn. So it's a quarter of that full turn. It's 90 degrees. We have gotten to where we start to define the size of our angles as a fraction of a full turn. If I have an angle, let's say that that's 41 degrees, what that means is that is 41 3/60ths of a full turn, of a full circle, if you want to think of it that way. We have some special relationships. Of course, that is a line because it's got an arrow on both ends, means it goes in forever in both directions. Anytime lines intersect, they form angles. The technical definition of intersect is to share a common point. How many common points? One common point. A common point. So these two lines intersect. Now, some notation here. I name any line by just naming 2 points that are on the line. So that line going horizontally there, I'm going to call it line AB. Like that. Line going vertically, I want to put points on it. I'm going to call them C, D. So that would be line CD. That little symbol above it that looks like a tiny little line is the line indicator, of course. Let's put in the point here. I'm going to call that point F. They intersect at point F. Now, right now, I'm calling this line here AB. I could call it line AF if I wanted to, because A and F are both on there. I could call it line FB. I could call it line BA. The order in a line doesn't matter when I name it. Same going up and down. I could call that line CF or FD or DC. All sorts of different names I could call that. I just have to name 2 points that are on that line in any order. Well, let's look at these and let's say that these two lines intersect to create one right angle or 90-degree angle. What do I know about all the other angles? They're all 90 degrees. They're all right angles. That is what we refer to as perpendicular. You know, we think of perpendicular as just intersecting at a right angle. That's sort of true. Perpendicular is actually just a little bit more powerful than that. Perpendicular means it's at a right angle in every possible measurable direction. Now, for two lines intersecting here, that's not a big deal. I mean, it's just measuring that one right angle and the other ones have to be. But perpendicular could also apply to three dimensions. Like if we have a plane, remember, is just a flat surface with a line coming out of that plane, going through the plane. That line is only perpendicular to the plane if in every possible direction that I can measure the angle, that line is perpendicular to that plane. Does that make sense? So perpendicular is just slightly more powerful than right angles. You could have a line cutting through that plane that makes a right angle in two directions, but not in the other. Next, we can have I could have a line that cuts through like this. There will always be a direction where I can measure that it's going to be perpendicular. Off to the side. I mean, the line's probably going like this, but it'll still be perpendicular this direction. And of course, on the opposite side, it would also be perpendicular. Now, I shouldn't say perpendicular. It would be a right angle on those directions. It won't be perpendicular means it has to be right angle all the way around it. So that's not perpendicular. It just has two right angles. So now here, these two lines don't cross. That's referred to as parallel. Now, most of us have defined parallel as two lines that never intersect. Well, that's partially true. In two dimensions, that works. In two dimensions, lines will either intersect or they'll be parallel if they're confined to that flat surface. But if they're not confined to a flat surface, if they're off in three dimensions, for example, if this is a line and this is a line, do they ever intersect? No. Are they parallel? No, they're not. To be parallel, the technical term is everywhere equidistant. That just means always the same distance apart. To talk about that, always the same distance apart, we should talk a little bit about how we measure distance. To measure the distance that these two lines are apart, you have to pick a point on one line. So if I pick this point here, I measure the distance to the other line from that line at a right angle to the other one. So if I pick any other point here, and I go make a right angle to the other line, the length of that segment will always be the same. So I might have this as being line AB, this here as being line CD. I would have line AB is parallel to line CD. Of course, up here for the perpendicular, line AB, that upside down T is perpendicular to line CD. I'm never going to quiz you on the notation, but it's notation you're going to see in the book as we're doing homework, and you might see it on a quiz. You know, I tell you that line AB is parallel to line CD. You need to know what that means because you're going to need that information to figure other stuff out. So we have these angles, and we've talked about the angle being a fraction of a full turn or difference in direction if we're using that absolute directional system. But how do we find that size? I mean, it's not always going to be labeled with its directions. Well, the tool that's used looks something like this. There you got her, a protractor. Now, a protractor, how much you're going to use it depends on where you end up in the field. You may or may not do some drafting or some quality control, but there is a tool that's called a universal bevel protractor that you most likely will use at some point. And so I'm showing you the protractor, not because I think the protractor itself is important, but I want to show you this before I build up to the next level, which is very important. Now, most protractors, the first thing about dealing with a protractor is you have to figure out where the zero is. Just like a ruler, you've got to figure out where the 0 point is to measure from. And in many protractors, it's not at the bottom edge. There's actually a point slightly up from the bottom. It's the 0 point. So that would be labeled 0 over here on the side. You'll notice there's that little star or crosshair in the center of that line. That's where the vertex of your angle has to go. Then, of course, measuring up, 90 degrees is going to be up here. And I suck at drawing these lines, so we'll try it one more time. We're going to call that close enough. So you can see these are numbered going up from each side, 10, 20, 30, 40, 50, 60, 70, 80, so on. They're also going to be numbered 170, 160, 150, 140, and so on. How do we know which set of numbers to use? Well, like we said, our vertex always goes right here on the crosshair. So if an angle comes in like this, is that going to, notice my vertex is on the crosshair. One side of the angle has to be on one of the zeros. Notice this cuts through the 50, but that would also be labeled 130. Would it be 50 or 130? It would be 50 because this is an acute angle. An acute angle is always less than 90 degrees. If I had one that came in like this, now that one, that's labeled 30 or 150. Which one of those am I going to use? That one I would use the 150 because that's an obtuse angle. The obtuse angle is always bigger than 90 degrees. So you should be able to tell by looking at the angle whether it's bigger or smaller than 90, and then that'll tell you which set of numbers to use. Where it would be difficult would be let's say it were like this, really close to 90. How would I know whether that's 93 or 87? Well, I look at the side that the initial side of that angle's at. If I'm at the 0 on this side of the protractor, that means I'm using the small numbers on this side and the large numbers on this side. Okay, well, so as I said, I'm not so concerned about using a regular protractor as I am about using a universal bevel protractor. A universal bevel protractor uses what's called a vernier scale. Now, we looked at a vernier scale a little bit last semester when we looked at calipers and micrometers and that, the old style vernier scale. Well, here's a case where we're going to have to figure out how to use the vernier scale. So a universal bevel protractor, what it is, it has that regular like half circle like a regular protractor does. But then it has an arm on it that rotates. And that arm Well, and one end of the arm will mark the angle up here on the protractor. The other end is used to lay on a surface. So you lay the bottom of the half circle on the surface, and then that arm on a surface, on a second surface. And what it does now is this will measure the angle between those two surfaces. So what you'll have is you'll have the regular protractor out here. And then you'll have the part that swings with this arm. That might look something like this. That might number up to 50. A lot of times they're numbered 5, 10s, or 15s. They'll be numbered in the other direction as well. So what we look for, yeah, pretend those are evenly spaced. What we look for is the one that lines up here. Now the first thing we do is we have to read the main scale. This up here is the main scale. We read the main scale at the 0 of the vernier scale. That's the 0. So what is that between up here? This mark is what? 46. And this mark is 47. So it's between the 46 and 47. Does not matter which one we are closest to, we go to the smaller one. So that's saying 46 degrees. What's read down here is something called minutes. Minutes are a fraction of a degree, and we'll talk about them more in just a little bit. And we look to see which one of these lines lines up with a line on the main scale. This one here appears to be the one that lines up the best. So what that's saying is 30 minutes. The symbol for minute is that single quote, like that. Not talking about that yet. So we can end up with something like this. I'm just going to label every third one here. So looking at this, where do I read the main scale? Yeah, here's my 0 on the vernier. That's 23 and that's 24. So we're going to take the 23. 23 degrees. Where do I read the vernier scale? This one here is probably the one that's closest to lining up, right? That'd be 10, 20. 20 minutes. So that's 23 degrees, 20 minutes. I have never seen a bevel protractor, at least a handheld bevel protractor that can go down to less. I think I saw one that went to 5 minutes. So 5 minutes, there's 60 minutes in a degree, so that's a 12th of a degree. Most of them I've seen go down to either 10 minutes or 15 minutes. So a 1/6 of a degree or a 1/4 of a degree. To get much smaller, that's really tough to do with a handheld device. Now, I have seen some that were lasers that went down smaller than that, and I have seen some that dealt with what they called refractometers or profilometers. I don't know if you guys still have one of those down in the shop or not. What it basically was is you'd magnify it. You'd put it in the on a screen, and there'd actually be a light behind it that would project it up onto a larger screen, so it'd magnify everything at a certain magnification. So it was much easier to see fine details like that. As far as it's simple, what's that? Yeah, that's one type of profilometer, yes. But it magnifies it so you can see those small differences. But in real size, real time, to go less than 5 minutes is really tight to do. Now on these, I've read both of them going in that direction on the vernier scale. It's very possible to have it line up, have something line up on each side. How do I know which direction to go? Well, for this one here, let's do it this way. That's not what I want to do. Ooh, that's not good. Well, looking here, of course, my 0 is right here. That's between what? 56 and 57. So we're going to use the 56 degrees. But we have this one here at 10 that lines up. Notice they're numbered in 5s now and not 10s, because this is a 15. That's 5, 10, 15. And we have this one here at 45 that lines up. How do I know which one to use? Well, in the main scale, what direction is increasing? Going that direction is increasing, correct? So then I go that side of the 0 is the direction I read. So it is the 10 minutes that I want. So that's 56 degrees, 10 minutes. So we always read the vernier scale in the same direction as the main scale would be getting larger. So since the numbers get larger going that way, we read on that side of the 0 of the vernier scale. Now, since my artwork sucks drawing those, I'm not going to draw out any more of those because I don't want to confuse you. But there are pictures in the book of those that we're going to do that I want you guys to make sure you are comfortable doing. Also, we've brought up these minutes. Let's talk about minutes. 1 degree is equal to 60 minutes. And of course, as Brad said, smaller than a minute is second. Just like in time, there are 60 seconds in a minute. So 1 minute is equal to 60 seconds. The symbol for minute, as we said, is that single quote. The symbol for seconds is the double quote. So you can see you may have to be a little bit careful here. That looks very similar to feet and inches. Like I said, in real application, I very seldom see things measured down to the second. Very, very seldom. So usually that involves lasers to get it measured that precisely. So we might have an angle that is 27 degrees, 18 minutes, and 12 seconds. This notation is referred to as DMS notation, simply standing for degrees, minutes, seconds. Compared to something called DD notation. DD notation stands for decimal degrees. So one of the things we want to be able to do is to convert from DMS into DD. To do that, just like if we had feet, inches, and sixteenths, and we were converting it all into decimal feet, we start with the smallest unit. In this case, the seconds, the 12 seconds. And we're going to convert them up to the next largest unit, which would be minutes. Well, how many seconds are in a minute? 60. So we're going to take that 12 seconds, we're going to divide by 60. That's 0.2. What that's telling us is that we can add 0.2 to our minutes. So it's still 27 degrees. It is now 18.2 minutes. Now we have to convert that 18.2 minutes into degrees. And we're going to divide that by 60. There are 60 minutes in a degree. So divide that by 60 is 0.3133, I believe. 0.3033, sorry. 0.3033. So that gets added to our 27 degrees. That's 27.3033 degrees. Now, if I were doing this on a calculator, I would actually do this all right within the calculator. 27 degrees, 18 minutes, 12 seconds. I would do this. I would start with that smallest unit, the 12. I'm going to divide by 60. Get the 0.2. My next unit is the degrees. I'm going to add that. Add 18 degrees, hit equals. That's 18.2. And now I'm going to divide that by 60. So I said 18 degrees. Add 18 minutes, I should say. Divide that by 60 to make it degrees. 0.303. And then I'm going to add my 27 degrees. So it gives me 27.3033. Always go a minimum of 3 decimal places. I usually go 4 decimal places with these. The reason you go a minimum of 3 is so that if you're going the other direction, you have minimal round off errors. I said 4 is usually what I go as a standard kind of. So the 27 degrees, 18 minutes, 12 seconds was 27.3033 degrees in decimal degrees. Well, what if I want to go the other direction? What if I have decimal degrees, 51.8635 degrees, and I want to get back from decimal degrees to degrees, minutes, and seconds? I reverse the process. I have the 51 in front of the decimal point. That's going to stay full degrees. So I take off the 51, subtract the 51. Now I have to turn that decimal degrees into minutes. There are 60 minutes. So I multiply by the 60. Now I have 51.81. I take the 51 off of there. That is my minutes. So I have 51 degrees, 51 minutes. Now I subtract off my 51. I have 0.81 that I have to turn into seconds, so I'm going to multiply by 60 again. 48.6. Now in seconds, it is okay to have 1 decimal place. So it's okay to list that as 48.6 seconds. I've never seen anything actually measured down to a tenth of a second. Usually I see things measured down to maybe 30 seconds, even with lasers. So, I mean, that's a pretty precise measurement to get down there. But you are allowed to have it there. If you rounded that to 49 seconds, I'd be okay with that too. Just like any other measurement, We can do operations with this. If we are adding 15 degrees, 27 minutes, 49 seconds, to 27 degrees, 52 minutes, 23 seconds, I start on the right and I work my way to the left, just like I do with any other number. 49 plus 23 is 72. Well, is that bigger than a minute? Yes. So I'm going to carry 1 minute. How many seconds did that 1 minute take out of there? 60, right? So that leaves me with 12 seconds there. Now up here, I've got 27 and 1 makes 28, plus the 52, that's 80 minutes. Is that bigger than a degree? Yes. So I carry 1 degree, and that took how many minutes out of here? 60. So it leaves me with 20 minutes. 15 and 1 is 16, plus 23 is 43, or 27 is 43. So that's 43 degrees, 20 minutes, 12 seconds. I might have 39 degrees, 15 minutes, 41 seconds, minus 12 degrees, 51 minutes, 48 seconds. Subtraction. I start on the right, work my way back to the left, just like always, and I can borrow if I need to. Here I have 41 minus 48, can't be done, so I need to borrow from the 15 minutes is now 14 minutes. How many seconds are in that minute? 60. So 41 plus 60 is 101 seconds. So 101 minus 48 is 53 seconds. Now I come back here, 14 minus 51, can't be done. I got to borrow. This is now 38 degrees. This is now 74 because that 1 degree contained 30 minutes. 74 minus 51 is 23 minutes. Then I just have 38 minus 12 is 26 degrees. What do you think so far? We can multiply. 16 degrees, 27 minutes, 41 seconds times 3. Well, 41 times 3 is 123 seconds. We can actually get 2 minutes out of that, can't we? Because it'd be 60 and then 120. So 2 is 120. We take that out, there's 3 seconds there. 3 times 27 is 81, plus 2 is 83. Can I get a degree out of that? You bet I can. That would be taking out 60. I get 1 degree out of it. 83 minus 60, there's 23 seconds there. Or sorry, minutes there. Now I've got 3 times 16 is 48, plus the 1 makes 49. 49 degrees, 23 minutes, 3 seconds. Technically, you probably should list it as 0, 3 seconds. Fill in the digits. Nope, that's just 0, 3. That's 3. There's no decimal point there. I just relist the 0, 3 because most displays have 2 digits allotted for seconds. So you'll see it displayed as 0, 3. We can divide as well. Let's say I want to divide this by Oh, let's say divide it by 6. 6 goes into 27 4 times. It'd be 4 degrees, right? 4 times 6 is 24. That gives us 3 degrees left over. Before I do my minutes, I got to take that 3 degrees, make it 180 minutes. Bring down my 19. That's 199 minutes. Six goes into 199. 33. That's 198. We subtract, there's 1 minute left. Well, before we bring down the seconds, we turn that 1 minute into 60 seconds. Bring down the 48. That is now 108 seconds. Six goes into 108. 18 times. So this should have been 33 minutes. This will be 18 seconds. Nothing left over. So 4 degrees, 33 minutes, 18 seconds. That one's probably going to take a lot more practice to get used to. But we're almost out of time for the day, so I'm going to give you guys some to work on. Fully expect to take some time tomorrow to go over the conversions and operations with degrees, minutes, seconds again. I'll also take some time to show you on your calculators how the built-in functions on the calculator. It's going to be out of a packet, page 266. 1 through 75, the odds, and I believe I have to give you a new packet for this.